Hello everyone, we got Holden Surratt, Jordan McPeak, and Ben Cedar here. Our presentation will be over pattern matching. In computer science, pattern matching is simply checking a given sequence of tokens or characters for the presence of the same pattern. Knowing this, I will now pass the mic over to Ben, who will briefly go over the paper we use as a reference.
The paper that we used is titled Pattern Matching by Gonzalo Navarro. In this paper, we review the most practical techniques to find patterns of different kinds. We show how regular expressions can be searched for with general techniques and how simpler patterns can be dealt with more simply and efficiently. The central subproblem in pattern discovery is to determine how often a candidate pattern occurs, as well as possibly some information on its frequency. He goes on further to discuss how finding how often a certain string happens or a certain pattern happens on a string can benefit a bunch of different causes. But one of the most difficult patterns to look for is a regular expression. Regular expression, we're familiar with those. It is the case where you have certain states, how they transition to other states, how they be concatenated and separated, and all these other things, and or added. In order to create an automation for those regular expressions, well, he has to resort to an automata. The general idea is to build an automaton, which is a finite state machine that will be fed with text characters and will signal the text positions where an occurrence finishes. The general process is to first build an NFA from a regular expression, then convert the NFA into a DFA, and finally use the DFA to scan the text. To build the NFA, he will use Thompson's algorithm, so that given a regular expression, he can build the DFA. Thompson's algorithm is summarized by this table. This table is a little beyond me. I'm not sure I'd be able to explain it. If I did, I'd just be misleading you. But from the result of that algorithm, he is able to build this NFA. Using this NFA, we can then find a DFA. A DFA has exactly one state that can be active at a time, and there is exactly one transition to follow per text character. Navigating that should be pretty simple. From the NFA we had above, we're able to get this DFA. Navigating that DFA to validate whether or not a string input is part of the regular language. It's on this subject that we wrote our program. To demonstrate that program, we have Jordan. Jordan?
So for our program, we wrote an algorithm that will take in a string that we give it, and it will check whether that string is generated by the DFA we create. So we start here with a prompt that tells you if you want to show your work or if you don't want to show your work. And for the demonstration, we're going to show our work. Now we're prompted to enter in the number of states that we'd like to use. We're going to use 3 states. Then it prompts for how many transitions you want to use per state. We're going to go with 2 transitions per state. And now for the transition number 1 for the first state. So from the first state, we're going to go back to the first state. And the second transition, we're going to go to the third state. And for the first transition in the second state, we're going to stay at the second state. And the second transition, we're going to go back to the first state. And for the first transition of the third state, we're going to go back to the second state. And the second transition, we're going to stay at the third state. Now we're prompted to decide whether we want, or what states we want to use as start states. So we're going to go ahead and use state 2 as our start state. And then we're prompted to enter in the final states. So we're going to use states 1 and state 3 for our final states. Then we get a table generated, a DFA table generated. As you can see, we have the 3 states, state 1, 2, and 3, and the F and S stand for the final state or start state. And we can see where each of those states go on transitions A and B by following the table. And then below we can see the additional transitions. So now we're prompted to enter in a string, and from that string we'll determine whether the string is in the language or not. So for this one, we're going to enter in the string AAAA, BB, AB, AABB. As you can see, following each transition from each state, we find out that W is going to be in the regular language. And now we're going to demonstrate one that's not in the regular language. And I've already entered in all the same information as before. So we're going to enter in the new string AA, BBB, ABBA. As you can see in our final transition, we go from state 3, and the input A ends up at state 2, which is one of our start states. Therefore, this string W is not in the regular language.
Thank you guys for watching our presentation. We will now take questions.